So by calculation, they have shown that in a real network, there are 5 motifs. In a random, they're around zero point 0.5 with a deviation of plus minus zero point 0.6. So the occurrence of such a motif is usually shown on either a scale of p-values or z-score. So in this context, a z-score, higher the z-score, more prevalent the network motif in a real network. Hence, more significant it is. Z-score is calculated by subtracting the number of motifs in the randomized network from the real network divided by the standard deviation. I'll come to that a little later. So that's the introductory part. Now, if you look at the types of network which I'm going to talk about today, there are basically 4 main types. There's simple regulation, the feed-forward loops, the single input module, the SIM, and dense overlapping regulons. Let me clarify for the record, there are a lot more types of network motifs than what I've mentioned over here. But these 4 are the most prevalent in the E. coli transcriptional network and which are most clearly defined. Furthermore, from these 4, the first 2 are really well organized and defined. The next 2, SIM and DORs, are a little fuzzy. Right. So now, the term simple regulation is self-explanatory. It means that the regulation is really simple, wherein one transcription factor, Y, regulates the gene X or the operon X, and there should be no additional interactions. Which means that protein Y regulates gene X, period. That's it. Now, on certain occasion, gene X tends to have a self-edge, in which case that would be called as an autoregulation. So autoregulation could be either repressive activity or an activation activity. So in this case, X represses itself, and in this case, X activates itself. This kind of regulation is called as a negative autoregulation, and this is called as a positive autoregulation. Let's look at them in detail. Now, is autoregulation a network motif? That's the first question which strikes our mind. And to answer that, we know what to do. We're going to check the occurrence of this motif in a randomized network and occurs in real network and see the significant difference. So when that's done in the E. coli TR network, the transcript network, they have found that there are 40 motifs occurring in a real network and around 1 plus minus 1 in a randomized network. So that's why the occurrence is really high, and hence it is termed as a network motif. So furthermore, in E. coli there are 40 self-edges, means 40 autoregulations, out of which 34 are negative autoregulations. So basically in E. coli, half of the repressors are NAR. Which means now, if you look at the NAR, the way how it works is pretty simple. You have a protein Y over here. Protein Y goes and binds to your promoter or operator, and it leads to your mRNA, which translates to your protein. Now this protein in this case will go and repress the own activity, own genes activity. Hence now this is a negative autoregulation. Negative autoregulation is shown to have few functional significance. In the first place, the genes which exhibits NAR tend to have a strong promoter, which means the production of the product is really rapid. The second point is the repression activity is dependent on something called repression coefficient, which is the threshold value. It's not that every time the protein is produced, it represses itself. It has to attain a certain threshold above which the repression activity starts. Another point to mention is NAR is shown to exhibit or is shown to reduce the cell-to-cell variations in protein level, which means if a cell has got really high protein level, that can go down and repress itself. If a cell has really low protein level, it can go and activate itself to produce some more. Hence, the cell-to-cell variation could be leveled out by NAR. Now, similar thing, but on opposite basis, which means now if this repression activity could be made into an activation signal, that would be then called as PAR, positive autoregulation. So protein Y binds to your DNA, it then goes for your mRNA, it goes for your protein, and then you have the activation. The effects are exactly the opposite. Now, if we look into the dynamic of this motif, now I've got the time axis over here, the cell generations, and then this is basically the number of products, the percentage of product from your real product divided by the ST would be over here, the steady state product. Now, this would be the simple regulation without any autoregulatory effect. Now we know that when there is a negative autoregulation, it speeds up the response. By the way, the term response time means the time, in a very simple view, it's the time the protein takes to reach its final level. In a more mathematical view, response time is nothing but T half, which means time taken for the protein to reach concentration exactly half of its steady state. So now, this would be the graph for negative autoregulation. You can see that it's a slight shift towards left. Similarly, this is a sigmoidal curve for your PAR. Now, if you look at the T half of your simple regulation is right in the middle, and T half of your NAR is a lot less than that, hence it speeds up your response time. And T half of your PAR is right to that, so it takes more time for it to reach at certain level of protein concentration. That's the dynamic of your NAR and PAR. The example would be seen in one of the later in vivo relevance of the motif. Now, the next motif seen in many of the networks map are or is the feed-forward loops, or there are different types of FFLs, which I'll be talking now. Now, in FFL, this motif is found like in a number of hundreds in the EcoM map, which gives it a lot of significance, and it's one of the most clearly defined network motif. In this motif, you have one factor, one transcription factor, which regulates another factor, and both of these factors together leads to production of one product. That's gene Z. Now, in this one, I'll be using the term X to indicate the main activator, then the secondary would be Y, and the product would be Z. Which means now this loop will have two arms. One arm will have two activators, X and Y, and the product Z. One arm will have the activator X and the product Z. Right, so this will be more clear if I show you the diagram. Now, as there are three interactions in FFL, so logically there are 8 probable FFL loops structure, so 2 raised to the power 3. And out of these 8, it is divided into two main subtypes. It's called coherent FFL and incoherent FFL. Now, the term coherent and incoherent is termed by looking at the effect of the main transcription factor X on Y. If the effect or the overall sign is similar, then it's called as coherent. And if it's not similar, it will be called as incoherent. In this type, for example, X to Y and then Y to Z, this whole signal is similar to this signal. Hence, this is called as a coherent FFL. Out of these coherent FFLs, type 1 is the most prevalent in equivalent network. So we'll talk about this motif. Furthermore, from the incoherent, type 1 is again the most prevalent, so we'll talk about this one as well. In fact, incoherent FFL is the main topic of the research paper which we have read. One point to